Hi guys, Dr. Diaz here again, and today we're going to discuss the area under the curve. Area under the curve. Basically what they want to do when you do working with problems area under the curve is to find the area, actually the area under the curve. Now, it is easy if you find the area under the curve if the geometric form you have is a rectangle or a triangle. And why is that? Because, look at this line here, because you know what is the area of a rectangle. It will be base times height, right? You have here the base, you have here the height. So the area of a triangle, of rectangle, is base times height. Or if this was a triangle, suppose that it goes something like this, then it will be the area is just 1/2 base times height, right? These are easy to find their area because their formulas are well defined. But if it's a curve, unless it's a circle, which it will be pi r squared, if it's a curve like this blue line that we have here, it's actually pretty difficult. The way you do this one, and the way that actually was done originally by Archimedes, like more than 2,000 years ago, it was using the method of exhaustion. You know, it's basically putting in a circle. If you have a circle, like we have here a circle, then you try to cover the area of a circle. Yes, assume this is a circle. A triangle. But still you have this space here, this space here, and this space here empty. What else you have to do? Well, you put a square. And then after a square, you put a pentagon, and then an hexagon, and then you keep going an n-gon. Because you want to cover the entire area of this by using what I said, the method of exhaustion, which actually was Archimedes, the one who tried to do it first. And you know how the story goes. The Roman soldier wasn't happy, and then knocking with a club. Well, the thing is, then 1,000 years later, and Newton came. Well, actually, Newton, Fermat, Descartes, and others came with the idea to do this, and we all know this. It's in Newton's book of Principia. Okay, so how we do this? If you have this thing here, the first thing you would do is put under this curve things that you know that are well defined, like rectangles. Yeah, you have rectangles, and the advantage of having these rectangles is you know the area. The area was base times height. The only thing you have to do is sum the number of rectangles you have here, right? Forget this one. Sum the number of rectangles. You have 1, 2, 3, 4, 5, 6, 7, and 8, and then, well, all of them have certain height and certain width. And well, you multiply base times height, sum all of them, and then you get more or less the area of this curve. But what it happens, you're still missing some parts here and here and here and here and here. So what you would do? Well, as you can see, now we have more rectangles, smaller than a moment ago, but more of them covering more area. Still, there's something else missing here. So what you would do? Well, of course, more rectangles. And you're getting very close to the area under this curve. Still, you have some spaces, so you keep adding rectangles and rectangles and rectangles. You go all the way to infinite. And that will be using the method of exhaustion. That will be summing all the area and getting the area under the curve. There's a way much easier to do this thing. Actually, it's not easy. It's a little bit complicated. But that's where we're going now. We're going to take in consideration all these small partitions. We're going to call this regular partition. From A to B. For this interval, the width of each subinterval partition is known as this, which we're going to call the delta x. So look guys, this is an important equation. You're going to use it a lot when you're using Riemann sums and stuff like that. Is this equation that the number of regular partitions is going to be, well, the area that which, when the width, you're going from B to A, divided by n, which is the number of partitions. Okay? And here is how you go by points and partition. You know, the first one, it will be x naught plus delta x. The second one will be x naught, the previous one, plus delta x. And the next one, if you go for x3, it will be what? And if you keep going, you will have x3 is equal to x2 plus delta x. x4 is x3 plus delta x. x5 is x4 plus delta x. x6 is x5 plus delta x. In general, xi is going to be always the original one plus I delta x. How is that? Because you know that the first one, look here, includes x naught plus delta x, and the second one includes x naught, which x1, which has x naught plus delta x, right? So this is another equation that's very important, very useful equation that you're going to use all the time and solving the problem. And look how the delta x will be the width of those rectangles that we showed you a moment ago, looking like something like this, small triangles going from 0 to 1, 1 to 2, 2 to 3, 3 to 4. And adding all those fx, which is the function, times their increment. It's like, think about the area of a rectangle is base times height. In this case, well, since it's not a rectangle exactly, it's a curve, it will be then the function, which represents the curve, times that increment. And the sum of all of them will give you the area under the curve, which here we have A4. And the general equation, this is the one we're going to work with. The one that it says that the area A is equal to here. This is the equation you want. This is the one we're going to work with, right? This is actually, let's say, a shortcut to solving all those increments, because it's supposed that they're infinitesimal. There's going to be gazillion of those. So it will be easy to use, have an equation that will solve this one much easier, and it represents actually what we're looking for, the area under the curve. So let's look at an example. Okay, look at this one. It says approximating an area using rectangles. Approximate the area under the curve of here the function. You look at some sort of parabolic. It's concave down because x squared here minus 2x squared is negative. On the interval 0 to 1 using 10 rectangles and then using 20 rectangles. So let's see what they did. Here it is. Now look here. You remember the function? F of x is equal to 2x minus 2x squared. And we're going to substitute that small increment of 0.1 because it goes from 0.1 almost to 1. And we substitute in the function 0.1, it will be 2 times 0.1 minus 2 times 0.1 squared, it will give you 0.18, and that's actually the number that goes here. Then when you go for the next one, which will be 0.2, you will get this one, which is actually this number saying here, 0.2, evaluating the function, you get 0.32, 0.3, evaluating the function, and so on and so forth, and the sum of all these small increments will give you 0.33. That will be the area under the curve of this function, this one, in which the increments goes only for 10 small rectangles, and they divided them from, let's say, because it goes from 0 to 1, 10 divided by, it will be 1 divided by 10 is 0.1 each of these. Now let's look at the next example. Now this one is when the area is using 20 rectangles. If you remember, we go back a little bit for the problems. This says for 10 rectangles and then by using 20 rectangles. So let's go forward. Okay, we did that one. Now here we use the same thing, delta x. Now we try to use here the equation. I will show you. I'm going to write the equation in a second. Yeah, voila, here's the equation, right? Something similar to the one we saw a moment ago. I'm going back. Yeah, this one that I told you a moment ago. That's very important. We're going to use here to calculate the area. Yeah, here without that line over it. So now let's go forward to that problem. And here the first thing is to use that equation that I told you is very important. The one I'm going to write now, which was b minus a divided by n being the number of partition. In this case, the number of rectangle 20. And if you remember, the interval goes from 0 to 1, right? That's why we put 1 minus 0. Get 1 over 20 is 0.05. That's delta x. Right? And the function xi is going to be delta x times I, if you remember the equation. This one that it says xi naught is equal to x naught plus I delta x. Remember, this one is always going to be a. And the interval a and b, this x naught is always a. And in this case, the problem we're doing is from 0 to 1, so we know that a is 0. So going back to that problem again, that's why we get here x naught, xi is equal to x naught plus delta x. X naught is a and it's 0, so it's going to be just delta x times I. Oh, I forget the I here. Delta x times I for I that it goes from 1 to 20. So the formula is this one. The area under the curve of those 20 rectangles is going to be from 1 to 20, or f of I xi times delta x, which is going to be, well, the function xi minus delta x. You substitute in the function, and voila. I'm going to show you how to do this one in a second. Next slide. Let me next video. Bye. See you guys.